Can you hear me? Good.
Okay, we're going to get started. Welcome. Welcome to our Fall 2024 APS Colloquium. It is my pleasure today to welcome Professor Carol Paty from the University of Oregon. She got her BA at Bryn Mawr, and then she did her PhD at the University of Washington. Professor Paty is a co-I on NASA's Europa Clipper mission, which just launched. That was exciting. And JUICE, which is the European Space Agency mission to Jupiter. She has served on many, many steering committees, including OPAG, which is the Outer Planets Assessment Group, National Academies, and a number of other review panels. And she has the exceptionally exciting intersection of being a modeler and a mission person. So a very special skill set. So please welcome Professor Carol Paty.
Thank you so much. Can you hear me okay? All good? Perfect. Thank you, Shannon, for the kind introduction. It is such a pleasure to be here. I love University of Colorado. I love LASP. I love all my amazing colleagues who are here that I've had the chance to know for so many years, and it feels like a wonderful opportunity to come and talk to you guys about not Clipper, because I figured you guys have probably been hearing about the whole Clipper launch thing from folks around here who are involved in the mission for at least the last 3 weeks nonstop. At least that's all I've talked about nonstop for 3 weeks. And so I was excited to talk about another solar system object that's near and dear to my heart, and that's exploring the magnetosphere of an ice giant, specifically Uranus. And what I've put up here to get us started, not a pointer, but I can use, if I use my cursor, can you guys see it up there? Okay, that's fine. That'll work. Is kind of an evolution of our thinking on Uranus as shown in a photo montage, right? So if you think about what we first saw when we looked to Uranus, when we flew by with Voyager 2, we saw a turquoise ball and some really fun rings. And we've been looking at it steadily using more and more exciting techniques, using the Hubble Space Telescope, using HST infrared, using Keck infrared with Chandra X-ray overlaid on it. So we've kind of, perfect, thank you. We've had this kind of evolving picture of Uranus, which is also kind of mapping, in my mind, our evolving thinking on Uranus as well. And of course, you can't end without showing some of the lovely images from JWST, which are, again, showing us Uranus through new eyes and new perspective. Decades and decades after that first and only encounter of Uranus with Voyager 2. So what I've done here is I've kind of put together what I think are some of the most exciting and interesting current thinkings on Uranus's magnetosphere, and some of them are reflections of my own group members' work, and some are a review of other folks' work. So it's a bit of a review with a little bit of bias towards my own students' work. And it has been a team effort. It's also been a team effort, and that I've been working with some folks on really trying to refine some of these science questions for why Uranus's magnetosphere is an exciting and interesting place that we want to go and explore and study. So just, I didn't put everyone's pictures up there because that would be ridiculous, but I put up the students' pictures and former students' pictures because, let's face it, they're the exciting ones that you guys should be tracking now. But here we have Xin Zhao, who actually was a researcher here at most recently, master's student Angela Olsen, recent PhD Joe Caggiano, and current PhD student Caitlin Donaldson, and all of them have been working actively on studying Uranus and Neptune's magnetosphere. And I'll occasionally stake in a little bit of Neptune stuff here too, because it's an ice giant, it's an interesting magnetosphere, and there's a lot we can learn from both of them, not just one over the other. So I've tried to keep it Uranus centered, but there'll be occasional Neptune biases thrown in. And why do we care? Why are we interested in having discussions about Uranus all these decades after Voyager 2 flew by and made those first and only in situ measurements of the system? Well, it's because recently we had a new decadal survey that came out. Several people in this room I know worked on it, including myself. And at the end of the day, the Decadal Strategy for Planetary Science and Astrobiology, or the OWL, Origin, Worlds, and Life, came to a really important finding, and that finding was that it prioritized Uranus Orbiter and Probe as the new flagship mission to initiate in this decade. Now, we can talk offline, or over a beer, or over coffee, about whether or not we think this really will happen in this decade or not, and what the ramifications of that process are. But the fact of the matter is that it was prioritized because the science was compelling across all the disciplines related to Uranus science. I'm going to focus on magnetospheres because that's what I do, and I don't know very much about other things because, like most of us who get our PhD, we become more and more myopically focused as time goes on. And we need students to break us out of those barriers. But it was prioritized because the science was compelling. And so before I dive deep into the Uranus magnetospheric science, I will take a step back first and remind us about magnetospheric science in general, and then maybe why Uranus provides this incredibly unique template, or this incredibly unique case study with which to compare against our Earth magnetospheric template. Right, so I'm guessing that some of you are familiar with the sun and the solar wind, most likely. And these are just some nice images of the sun and the sun's atmosphere, the corona, when in eclipse. Did a recent eclipse pass over Boulder? Not any of the recent ones? No, you guys have been totally SOL. I'm so sorry. That is a bummer, because when you have the opportunity to see a complete solar eclipse, it's really special. It's one of the few times, or only time really, we can look at the sun's atmosphere with our eyeballs without burning our retinas out. And we can see it, and we can see beautiful structures in the solar atmosphere, not modulated by gravity, which most atmosphere shapes and structures are modulated by, but as modulated by the local magnetic field structure, organizing the solar wind or the sun's atmosphere. And we see that on kind of this large scale here when in eclipse, and when we look at the entire corona, and we see that when the sun is particularly active, right? When magnetic activity on the sun, sunspots, solar flares, coronal mass ejections occur, and again, you have this magnetic modulation, this magnetic-driven activity that enhances the solar wind. By the time the sun's atmosphere, streaming away from the sun, threaded with the magnetic field that we see highlighted in these images, reaches the Earth, the magnetosphere, people can yell at me if I get these numbers slightly wrong. This is my average take on it. The average density of the solar wind is about 5 particles per cubic centimeter, or essentially the best vacuum you've ever seen on Earth, right? It's the vacuum of space, but it's an incredibly reasonable solar wind density. The speed, on average, about 350 kilometers, ranging plus or minus, especially on the plus side when things are more active, like right now, up into the 800, maybe even up to 1,000 kilometers per second. And the magnetic field orientation varies wildly. anywhere between -10 and 10 nanotesla probably, with respect to the Earth's magnetic field orientation. So this is the driver for magnetospheric dynamics, right? This is a dynamic pressure of magnetized plasma that sweeps past the Earth's magnetic field, moving supermagnetosonically, faster than the magnetic sound speed, and therefore creating a shock when it runs into our Earth's magnetic field, right? And there's a great, there are great graphics and movies about this, I think. Hard for me to see the little arrow thing to hit play. But this is one of the nice ones that I like to show, because in 30 seconds I get to teach you all of Intro to Space Physics with pictures, right? So the sun's atmosphere is streaming away from the sun, moving at hundreds of kilometers per second and making its way to the Earth's magnetic field. And when it runs into this obstruction, moving at Mach 10 or so, it creates a shock. And inside that shock, you get shocked heated solar wind plasma in the magnetosheath, and you get the solar wind's magnetic field reconnecting or interacting with the Earth's magnetic field when it is anti-parallel. That magnetic flux is convected over the field. I'm going slower than the movie, and is re-added back to the magnetic field. So it's eroded off of the day side and re-added back in the night side through magnetic reconnection again, this nice symmetric process, and convected back to the day side. So magnetic flux is conserved, and also plasma is energized. And that energized plasma is what you see highlighted here, as having mapped back down to the Earth's atmosphere and creating the aurora that we all know and love. And maybe recently, because we're close, or actually I think now officially at solar maximum, we've been having more and more auroral events that much of the continental US have actually been able to see. I think even down here, a few events recently have been really visible. In Oregon, we battle the clouds, but sometimes the clouds cooperate and then we get to see the aurora too. So that's intro space physics in 1.5 minutes. And if I've gone over things quickly, it's because I really want to get to Earth as a template so that we can go beyond it, right? But this is, now of course it'll play on command. This is the snapshot picture of the magnetosphere. And just to remind you of some of those boundaries I mentioned, right? You have a bow shock because you have a super Mach flow running into this obstruction, this magnetic obstruction. You get a magnetosheath of shocked, heated, turbulent plasma that's being diverted around a pressure boundary. And that pressure boundary is the magnetopause, where the dynamic pressure of the solar wind is balanced by the magnetic pressure of our wonderful magnetic field that essentially shields us from the majority of the solar winds, abuse, and creates this cavity in the solar wind dominated by our magnetic field and a lot of plasma sourced from our own magnetosphere. I'm seeing smirks from Fran, but and this structure has this system has structure, right? It's compressed on the day side from the solar wind, elongated on the night. And the reason that structure is so large, if you think about a dipole magnetic field at the Earth, it would fall off as 1/r cubed, and its influence would not extend out all the way to our moon and beyond, right? But because of this interaction with the solar wind, dynamic currents are generated that kind of structure and sustain this entire system, this structure in the tail, and it extends on, like I said, past our moon. In the case of Jupiter, which I'll talk about just for one moment, it extends multiple AU beyond Jupiter, and traces of it were even seen upstream of Saturn during the Voyager encounter because they were nicely aligned, which was why we had the Voyager mission when we did. So that is our template, this guy, right? A nice dipole field interacting with the solar wind. And then we can think about larger magnetospheres like Jupiter, and I won't dive into Jupiter too much because there are some real resident experts on Jupiter's magnetosphere in the room. They're all sitting over there. But I do want to highlight it because it provides us a step in a direction from the template, right? It's a large, rapidly rotating magnetosphere, and it has a 10-degree dipole tilt relative to its rotation axis. And it also, part of what motivates Clipper and Juice, has the Galilean moons embedded deep within it, Io, Europa, Ganymede, Callisto. And they all are embedded deep within the magnetosphere. They don't really sense the solar wind very much. And their entire upstream is dominated by whatever is going on at Io and whatever is going on in Jupiter's magnetosphere. This 10-degree tilt turns out to be quite fortuitous, actually, for studying the icy moons, because it creates this beautiful sinusoidal magnetic wave upstream of those moons that enables us to magnetically sound the interior of them and discover things like subsurface oceans at Europa. And this is just highlighting that because of that 10-degree tilt, which is in cyan, the magnetic equator is oscillating up and down over the rotational equator, which is the plane in which the moons are orbiting. And so what you see driven at, in this case, Europa, is an up and down magnetic wave there as the magnetic equator sweeps over every 11 hours or so at Europa. Again, nature provides the wave, we provide the spacecraft to measure the inductive response of that wave, and then a bunch of modelers get together and say, okay, what does that inductive response actually mean in the subsurface? Is it a liquid ocean? Is it someone being really nasty and wrapping the interior in copper wire? Whatever the case might be, we can model it out and figure out the conductivity, thickness, and ice shell thickness above the ocean, and hopefully with 49 flybys disentangle that complicated problem with great precision. To say, all this to say, this is a tilted magnetic axis, an example of a large magnetic field that's tilted 10 degrees and creates a really nice system to study icy moons as well. This talk is not about Jupiter. It's about the ice giants, specifically Uranus, but the ice giants I'll cover just for a moment together, because the last time we visited them was with Voyager 2 in 1986 for Uranus, 1989 for Neptune. And they are really far. Like Jupiter seems far away. It's going to take us 6 years or so to get there with Clipper. These are really far away, 20 AU, 30 AU away. They take a while to get to, which is a big reason why we haven't been back. But we did get to visit them with Voyager 2, and this is just a reminder of where Voyager 2 went. It left Earth, flew by Jupiter, flew by Saturn, then out to Uranus and Neptune. Voyagers did not orbit these planets. They just flew by. So all the information we have from in situ measurements at Uranus and Neptune has come from singular flyby, a snapshot in time for temporally and spatially variable systems, which have still fed and fueled a wealth of questions about how they interact and how they exist the way they are, which makes them somehow even more attractive to go back and study because you just don't know enough, and it makes you want to go back and learn more. So a bit about these magnetospheres. I said we talked about Jupiter as an example of a nice, big, rapidly rotating, tilted magnetosphere. And these are what have been referred to as, well, tilted and offset magnetospheres. I like to just refer to them generally as asymmetric magnetospheres. And there's a reason for this. If we look at what was obtained after the flybys, oh, some letters are missing. The last letters are missing from each of them. How very odd. That's quite special and unexpected. They were there earlier today. I mean, at least it was equally treated. They each lost a letter. So the magnetic fields were observed to have really large tilts relative to their rotation axes, right? A dipole tilt of 60 degrees for Uranus, of 47 degrees for Neptune. These aren't just a little bit tilted, they're really tilted. And then there's this other definition, this offset. What does an offset mean? Offset means that if you were to look at these magnetic fields like dipoles, you would have to shift the center of the dipole off the center of the planet, not by a little, but significantly, by a third of a Uranus radii in the case of Uranus, or for half radius with Neptune. From a conceptual perspective, this doesn't make sense because you, me, and the lamppost know that the dipole magnetic field is not a bar magnet sitting in the middle of Neptune or Uranus or Earth for that matter, but that there's a dynamo process at the Earth, a liquid outer core that's convecting and undergoing Coriolis forces and turbulent, an MHD fluid, a conductive fluid that's generating the dynamo magnetic field of the Earth. At Uranus, Neptune is a bit more complicated because it's not a liquid outer iron core. That layer that the dynamo is being generated in for these planets is much closer to the surface. So what we're actually seeing here, and I'm getting slightly ahead of myself, is really a nice graphical representation of what a dipole plus a strong quadrupole and octopole moment looks like. And you can do it if you just sketch it out on paper. If you have just a dipole and you add a quadrupole on top of it, one part of the dipole is going to be enhanced a bit, the other side is going to be minimized, and that's going to express itself at distance as being a shifted or an off-centered dipole field. When you get closer in, it's another story. Okay, but this is the cartoon. This is the picture we had after those flybys for both Uranus and Neptune. And if you want to look at what the data really told us, and I think it's always nice to go back and look at the data, this is the flyby of Uranus. You can see we came in from the sunward-facing side, crossed the bow shock and the magnetopause, got as close as we were going to get to Uranus, right about here, and then flew out, crossing the magnetopause and bow shock boundaries on the wake side, right? And what it looked like was this. Like I said, we were flying out in the solar wind. The solar wind was actually 0.1 nanotesla upstream of Uranus, which was a little more than was anticipated from Parker spiral models. In the past, it had even been modeled with no solar wind magnetic field. But it was about 0.1 in the negative z direction. And then you can see very clearly we passed the bow shock and the magnetopause, and then we're in this nice dipolarish looking field. And then on the way out, we had a couple of these neutral sheet crossings. This was part of the real intrigue here, is if you have a really highly tilted off-centered dipole, and also the rotation axis is pointing at the sun, you get this tumbling magnetosphere. And what that means in the wake is a really complex geometry. And I think when I use the word asymmetric magnetosphere, what I really mean is a really complex geometry, which is formed from all these contributions of high tilt, off-centeredness of a representative dipole, and obliquity too, which we haven't gotten to yet. If you were to compare Earth's radial component of the magnetic field, which is going radially out in one hemisphere and in the other, creating a very nice dipole field, at Uranus you'd see something a lot more complex in terms of the radial structure, highlighting the fact that you have higher order moments, quadrupole and octupole, contributing to the local field structure near the surface of the planet. And if we take that a step further, this is what I kind of summarizing what I've said already, so I won't read through it, but it's just to say that highly asymmetric fields can be represented as off-centered tilted dipoles when you're far away, when you're looking at magnetopause or bow shock boundaries. But the closer you get in, it starts to become less reasonable to treat it as an off-centered tilted dipole, because those higher order moments become stronger, right? Dipoles fall off, like we said, as 1 over r cubed. Quadrupoles is 1 over r to the 5th. Octupoles is 1 over r to the 7th, which means the further out you go, their influence is minimized. The closer in you get, you start to really see the contribution of those fields. But the off-center tilt dipole is not bad for doing things like understanding the standoff distance of the magnetopause. It does a good job representing that, and even the variability as it's rotating and tumbling along relative to the solar wind, and varying the strength and depth of the cusp, right? Because if you're rotating pole on and pole off, you're going to be really changing the location of the cusps relative to the solar wind. The implications also have some really interesting, there's interesting ramifications or implications in terms of the tail, right? The shape and the curvature of the plasma sheet that we'll talk about in a bit more detail as well that come from this. So again, this just has Earth, Uranus, and Neptune, the radial field components, again, as a reminder of just how non-symmetric, non-dipolar these fields really get close to the planet. And then there's obliquity, which I mentioned before. And with obliquity, we realize that we've got Earth and Saturn, Jupiter, we know very well. Uranus is really the outlier here, 97.8. That basically means it's pointing at the sun, essentially, during solstice, right? And it's rotating side on during equinox. So you guys get to be the sun. This is solstice. It's rotating around like this. Equinox this way, which is really different from what we're used to thinking about in terms of seasonality. And just as a reminder, even a little bit of obliquity has influence on the magnetosphere. So for Saturn, for example, we found with Cassini that the magnetosphere, the magnetodisk was bold, was curved up, depending on the seasonality or how the tilt was with respect to the solar wind, because the solar wind was kind of pushing up from the bottom and adding that curvature, right? And that changed with season at Saturn as well. So now imagine these higher obliquity structures and the fact that at Saturn the field was nicely aligned with the rotation axis, and here it's definitively not for the ice giants. And this is just what I articulated with interpretive dance, thinking about what equinox versus solstice means as a body is rotating relative to the direction of the sun and solar wind. And the time scales involved for Uranus here, equinox was in 2007, solstice is coming in 2028. The seasons are long. We have a long time period to observe those seasons. And so I'm actually going slower than I thought, so I hope everyone is absorbing what I'm saying. That's okay, though. Again, we think about the tail, and this is just a mishmash of observations and models from that little one-dimensional slice through the tail. And what I love to think about for Uranus is that Uranus gave us a gift with this crazy asymmetric magnetosphere, because we had a one-dimensional fly through the tail, but we actually sampled a lot of magnetic latitude when we went down tail, because the whole magnetosphere was tumbling and rotating. The entire tail was helically rotating essentially as we went down it, which is why we kept crossing the neutral sheet in the tail. Even though we were just flying down tail, the whole thing was rotating helically as the spacecraft was going down, which is kind of represented here. If you unfurl the tail and put it in the perspective and put it in spacecraft land instead of rotating tail land, you get this, right? You get this kind of spiral motion of the spacecraft, which of course the spacecraft did not do a spiral motion. But if you undo the helicity of the tail and put it in the spacecraft, instead, this is what it would look like. And here's mapped out that curvature of the neutral sheet that we were crossing over as we flew down the tail. It's kind of amazing that we had that benefit to sample all these parts of the tail due to the geometry of the field. And there were model studies of this. This is by Gabor Toth. This was, again, one of those models that assumed the magnetic field in the solar wind was zero and just dynamic pressured the solar wind against this rotating magnetic field. These were some models that my grad student Xin Chao did back in 2017, doing a slice through of the tail, and I'll highlight this because it's a complicated geometry to get your head around. But basically doing a slice through of the tail, like here, and mapping out where that neutral sheet was and how it rotated around. These studies here, I really love. This is by Gina DiBracchio and Dan Gershman, because they took our Cassini eyes that were trained after looking for plasmoids in the tail of Cassini data, or in the tail of Saturn's magnetosphere and Cassini data for over a decade, and said, wow, we really know how to detect plasmoids now. And then they turned back and looked at that Uranus data from 1986 in high resolution, and they were able actually to pick out a plasmoid in the tail that had previously been missed, because we just didn't have plasmoid trained eyes looking at that magnetometer data yet, the way over a decade at Saturn looking for plasmoids in the magnetometer data enabled us to do. So yes, there's been a lot done about looking at the tail and the implications of the asymmetric magnetosphere, both from modeling and in the data, looking at the plasma sheet, the helical twistiness of the tail, the plasmoids, and cusps and magnetopause boundaries. And this is just, again, I'm gonna brag on my former student a little bit because it was a beautiful paper looking at this multi-fluid MHD model of Uranus. These are streamlines of the solar wind. You can see the off. Wow, there's some really weird thing. This is not an animation. It's just being fun over there. But the whole magnetosphere is rotating and tumbling and creating this fantastical structure to study with models and hopefully in the future with spacecraft. And he made some nice images, again, thinking about what it means to be in a magnetospheric system that tumbles with respect to the solar wind, right? The rotation axis. The solar wind on this is coming in from this side. This is equinox, so the rotation axis is in and out of the page, and you can see the whole magnetosphere is tumbling with respect to the solar wind, kind of going pole on, pole off a little bit there, and getting a sense of how that would influence the location of the cusps, the shape of the upstream boundary, over very rapid timescales. It's a rapid rotator for such a large system. And it's hypnotic. You can stare at it for a long time and not get bored, but you would get bored eventually. And this is, again, just a reminder of how these images came to be. We took a slice through the tail and kind of tracked over a rotation period where the neutral sheet went and that it was curved and kind of rotated around. And you could do this slice at multiple locations down the tail and get a sense holistically for how this helix was rotating around, even at distance. And then the more recent study that he did in 2020 was looking again at how that magnetopause boundary changed and how the cusp depths change as a function of rotation and as a function of season. So the last thing I'll touch on that was in the data was really the plasma observations. And this gets a bit tricky because these magnetospheres were incredibly absent of plasma, especially in the thermal plasma regime. There was very little plasma in both Uranus and Neptune, but arguably less at Uranus. But there were strong electron radiation belts, which indicate that, and they have to come from somewhere, right? You usually would expect or anticipate some seed population of plasma that's then accelerated and becomes trapped. But we didn't really see a whole lot of seed population because we really were looking at a vacuum level magnetosphere at Uranus for at least a large component of it. And then there were also low energy ion densities. Sorry, that's just what I was saying, is that there were really low iron energy densities in the magnetosphere. And so there have been re-examinations of this data by Ian Cohen and by others that kind of looked at perhaps, maybe, possibly there might be a small source of energetic particles that resided in between Miranda and Ariel. I think that this is a really good start at re-examining the plasma data, but I don't think it's definitive yet because it doesn't fully complete the picture. Even within their own paper, they said, yeah, well, actually this is like 6 data points. And so we really need to dig in and do a lot more work and think about how these populations are injected into the system and move through the system and gain energy in the system, and not just wave our hands and say wave particle interactions did it, right? We need to really understand the system in a bit more detail. One thing I like to just compare, though, between the different planets, right? Jupiter has an Ioplasma torus. Again, won't dwell on it because we've got the experts in the room. But that is a really localized source. And I say localized, roughly speaking. Neutrals come from Io, but they don't last very long. Like, they get ionized within less than an Io orbit for the most part and become the Ioplasma torus, and then are radially transported in the system. At Saturn, the picture is a bit different. You have this large neutral cloud from the E ring and Enceladus that expands out from about 3 Saturn radii to 8, 9 Saturn radii and has a pretty thick scale height off of the equator too. That's a cold neutral source that becomes ionized in a more distributed fashion throughout Saturn's magnetosphere. So a very different type of plasma source. At Neptune, maybe we see a source, possibly. Maybe a Triton neutral cloud, pretty hard to say. But at Uranus, gosh, it went from not very much down to even less in terms of total ion density along the L shell. And so where is the population coming from that's creating these electron radiation belts? Where are the ion radiation belts that would be symmetrically expected to be there with them? These are all pretty open questions in terms of what's going on. And there have been some new studies, and one of the studies is actually an Earth study that my grad student Joe Caggiano did, which is thinking about the role of non-dipolar fields when thinking about the plasmasphere and stably trapped plasma within the magnetosphere. So canonically, if we think about Earth, we think about a region around the Earth that is kind of co-rotationally bound, where the co-rotational electric fields keep the plasma nice and neat inside the plasmasphere, and outside the plasmasphere is convection electric fields take over and move the plasma around day side to night side, right? And this is a very nice picture, and you can balance them out and figure out where the plasma pause boundary is. When you're dealing with quadrupolar fields, it gets a bit more kinky. One, because quadrupoles come in different flavors. So first you have to decide what flavor of quadrupole you're dealing with. And then think about, well, where's the magnetic equator in this picture? Where are particles, where do we even do this balance of co-rotation versus convection? And so if you try to draw out the magnetic equators for 3 representative flavors of quadrupoles, and then map onto that balance between convective and co-rotational electric fields, you end up with something a little bit funky. And the best case scenario right? You end up with a very narrow, two-sheeted view of where plasma can be co-rotationally bound into pseudo-plasma spheres, and the convection is really pretty important and strong here. So maybe not a lot of plasma is stably trapped. And in some cases, for this type of quadrupole, you basically don't have a stable plasma sphere because convection ends up going all the way down along certain planes here and would erode away the plasma completely. So it's weird. Quadrupoles are uncomfortable because they break the symmetries that are so nicely highlighted in our space physics textbook about where convection and co-rotation balance and how plasma gets stably trapped, right? And if we look and just do a quick, I made Joe do this, he didn't publish it yet, but I made him do it for his thesis, just to say, like, where is it important? How close in do you have to get where quadrupole fields start to become important and you can't really just call it an off-center tilted dipole? What's the over-under on it? He made some maps just looking at the difference between the off-center tilted dipole and the quadrupole field model to see where those effects are most significant, right, where we start to get into the difference being on the order of a few orders of magnitude of nanotesla. Like not just a few nanotesla, but like hundreds or 1,000 nanotesla different in terms of the structure. And then kind of a ratio difference, the log percent difference. And again, even out, out to 20 Uranus radii, it's not all that much, but in certain planes on certain geometries, it starts to become pretty important. And then remember, this whole thing has to rotate. So it becomes not trivial to just ignore the quadrupole terms, especially when you're thinking about plasma stability. And that was the main takeaway from this. And he compared a bunch of different, when is the offset tilted dipole versus offset tilted dipole plus quadrupole most reflective of the data, and at what season. And you can see up close, or, they provide a lot of different realities depending on whether you're in solstice or equinox. Obviously, the best fit one for the blue Voyager data is the dipole plus quadrupole at solstice. That's where they match up the most close to the planet. But overall, at distance, they cover a wide range. At distance, it's not as important. Almost the seasonality isn't quite as important as you might think, which is a bit of a surprising result. And the last thing I'll touch on that was observationally modulated, or observationally driven, is the fact that Uranus's thermosphere and atmosphere are weird. And I'm not an atmosphere person. I'm barely a thermosphere person. But what we noticed, I'm pointing at this instead of up here, my apologies. What we noticed is that the temperature of Uranus' upper atmosphere is hotter than expected. And maybe it's not unexpected because all the giant planets seem to have a bit of an energy crisis in terms of the temperature of their upper atmosphere. But one thing that's unique to Uranus is that it appears to be steadily cooling for more than 30 years of observation. And that's a bit odd because it doesn't align with seasonality the way one might expect, or distance from the sun or solar cycle. So now the question becomes, well, is the atmospheric temperature really driven by particle precipitation and heating at high latitude, magnetic latitudes, wherever those might be on these planets, because magnetic latitude is weird? Or is it internally driven? Is there something in the atmosphere that's driven up by waves interacting up from the atmosphere and into the thermosphere? We don't really know the answer to that. We have limited auroral observations at these bodies because they're far away for Hubble UV to observe. We did observe the aurora when Voyager 2 flew by, and it looked kind of patchy, but the resolution was kind of patchy too, and we're talking low counts. So there have been several auroral observation campaigns that have revealed aurora at Uranus, but nothing like the other planets, and part of that might be a function of distance and sensitivity, and part of it might just be that it's different because it's not a dipole field, nice and symmetric and happy. So, oh shoot, yeah, there was one more thing that's really different. Right, the solar wind interaction at Uranus is also really different. And a lot of that is because of the fact that if you think about normalizing solar wind interactions from the Earth, the further out you get in the solar system, the speed stays constant for the solar wind. Nothing really slows it down, right? But the magnetic field drops off and the plasma density drops off, and that means the Alfvénic Mach, or the Alfvénic speed changes, right? It falls off the further out you go, and that means the Alfvénic Mach number is actually pretty high out in the outer solar system. This interaction is a bit different than all the way back at the Earth, and can lead to perhaps not the canonical global magnetic reconnection and convection system, the Dungy cycle that we're used to thinking about, but perhaps a more viscous interaction, one dominated by Kelvin-Helmholtz instabilities along the magnetopause instead of this global convection reconnection cycle. And he highlighted this in his paper by just showing that the further out you go, you're less able to stabilize Kelvin-Helmholtz instabilities. That means you're more likely to grow them, and you're less likely to have magnetic reconnection occurring because you have weaker reconnection electric fields. That's what's highlighted in red. So weaker reconnection electric fields and weakened ability to stabilize Kelvin-Helmholtz growth. You know, you might have some place where you switch over modalities between reconnection-driven systems and Kelvin-Helmholtz-driven systems. It's hard. We see Kelvin-Helmholtz instabilities at Earth. We saw them at Saturn. Maybe saw them at Jupiter. We've modeled them at Jupiter. We've seen them at Jupiter. Fran's nodding, right? So there's not an easy normalized, like, from this point forward, right? It's not like, and here is where Kelvin-Helmholtz takes over, right? There's something more nuanced, something more specific as to how these interactions occur, because we see Kelvin-Helmholtz instabilities all the way at the Earth and at each of the other bodies. But we also know that this is true in terms of the solar wind driving parameterization and what we would expect to occur at these boundaries further out in the solar system. And just if you like reconnection and you want to take a look at the most glaringly painful red stoplight images that you've ever seen in a paper, these just highlight when you have satisfied the two criteria for magnetic reconnection to occur, diamagnetic drift and flow shear onset. That's what's done here is the diamagnetic drift condition. This is mapped across Uranus's magnetopause. This is when flow shear is mapped across Uranus's magnetopause. And if you add them together, because you need to fulfill both criterion, you get most of the time magnetic reconnection isn't enabled, only in some very specific regions. And of course, as I've mentioned before, the magnetospheres are rotating and tumbling, and therefore magnetic shear is really a function of time and location across the magnetopause, not just time, but time and location. And recently, I threw this problem at some grad students in my group and said, okay, so these master's papers for Uranus and Neptune evaluated where reconnection can occur. Let's do the opposite. Let's evaluate where Kelvin-Helmholtz instabilities can grow along this magnetopause boundary. So again, you have this magnetopause boundary, plasma flow coming in, being deflected across that boundary. It's a little weird because it's in like a slice out of a 3D image, right? But what you're thinking about here is that you have a solar wind plasma flowing across the magnetopause. You have the magnetopause boundary, and then you have the magnetospheric plasma and magnetic field inside that boundary. And it's the shear between those two different regimes on opposite sides of the magnetopause where you can calculate whether or not Kelvin-Helmholtz instabilities will grow. So we basically created these paraboloids, kind of one inside of the other, representing both sides of the magnetopause, and calculated when this criteria was met. When could Kelvin-Helmholtz waves grow? And we did this for seasons. We did it for rotation phases. We did it for every possible, several orders of magnitude variation in solar wind, because why not, in terms of the magnetic field strength, just to see how sensitive the system was to all of these different factors, because they all play a role, right? All of them are playing into the velocity on both sides of the boundary. One is the magnetosheath, two is inside the magnetopause, right? The magnetic field in the magnetosheath and in the magnetopause, right? They're both being modulated by either the solar wind magnetic field strength or the rotation phase of Uranus, or the season of the whole geometry of the system altogether. And what she found, she did this for Uranus and Neptune, and chose slightly less offensive colors in my book, but maybe you don't like magenta and black instead of red and green Christmas tree stop signs. But what she found is that the magenta represents where Kelvin-Helmholtz are enabled. And again, here we're looking at solstice on the top for 0.01 up to 0.5 nanotesla, so kind of covering a pretty wide range. And then for equinox on the bottom half of this plot, and then rotation phase is mapped across. And what she found was that rotation phase doesn't actually matter a whole lot. Magnetic field strength of the solar wind, that does matter quite a bit, right? you know, that's a big difference in terms of the area across the magnetocause where Kelvin Helmholtz would be enabled to grow or not. And if you mapped it out in terms of the surface area allowed, again, broken down by the magnetic field strength and daily rotation angle, you can kind of see the stronger the magnetic field, the more Kelvin Helmholtz instabilities are enabled. The weaker the field, the less surface area enables Kelvin Helmholtz instability. So if we're close to the time, if I just take a step back now and review, what are the most important questions? I've given you a really broad overview of all the things we've learned from the original Voyager data, kind of a bit of a rapid sweep through of the types of modeling contexts people have built, from 3D multi-fluid MHD type models to analytical models, trying to understand every last aspect of the magnetosphere we can think of. We're left, I think, with some really compelling questions, right? One, I've just gone over, so I'll start in reverse and say, determine whether the dominant solar wind driving of Uranus's magnetosphere is by global magnetic reconnection or a more viscous-like interaction. Will we be able to have some sort of quantitative turning point, some metric for inflection where we can say, when it's like this, it's one way, when it's like this, it's the other? Will Uranus provide that case study where we can study that in detail? Another question is to determine which either magnetospheric or atmospheric influences dominate the long-term thermal evolution of the thermosphere. That's the one I touched on the least, because it's auroral observations and temperature observations and not particles and fields observations the way I'm used to thinking about them. But it's still a really interesting question, and it begs us to understand where the energy balance is for the thermosphere. Because it's something we can observe, and it's something that's mysterious, and it's something that's non-linearly related to solar cycle, distance from the sun, or seasonality. And we don't have a whole lot of magnetospheric plasma measurements or aurora observations to tell us the other half of the story. We want to determine how Uranus can support some unexpectedly intense electron radiation belts when we don't seem to really have a seed plasma population present. It's not just a little bit. And I hate this plot. I'm just going to say it. I really hate this plot because it doesn't make any sense to me, but it's used a lot, so I'm going to put it up there. For arbitrary reasons, if you draw a line from Jupiter, Saturn, and Neptune, Uranus looks different than them arbitrarily on this plasma density versus max MeV electron density. But it is true. The electron radiation belts at Uranus, if you explore their energy spectra, look a lot different than the other planets. And we don't have a source population of plasma obvious to support them, right? We don't have Io pumping all this material into the magnetosphere that then can be accelerated and energized and cracked. So where are they coming from, and what wave interactions are generating them? And then lastly, and this is the one that I think really is why Uranus is going to be a mission of discovery, not a discovery class mission, but a mission of discovery, is because we had a one-dimensional fly-through of a system. We spent how many years orbiting Saturn with how many orbits? And we still don't fully understand all the magnetospheric dynamics, sources, radial transport, all the processes involved in Saturn's magnetosphere. We have a much better handle on it than we did from Pioneer and Voyager, but it still has open questions that we've been trying to resolve. Here, we barely have a snapshot in 1D in time, and we didn't see a whole lot of plasma, but we know that there's rings, ring atmospheres, and moons, and we want to understand how plasma is sourced, how it's transported, how it's trapped, how convection versus co-rotation on a complex magnetic field works. We don't have another example that we've studied in detail. So instrumentation, I just put a list of instruments up here that I think would be a beautiful suite if we only cared about Uranus's magnetosphere with UOP. Fran, can we only care about the magnetosphere with UOP? Okay, but I care about the magnetosphere, and Fran cares about the magnetosphere. I'm pretty sure Andrew might care about the magnetosphere. I haven't talked to him in detail about Uranus yet, but we will. So if we were only trying to do a magnetospheric mission, and include the atmosphere because thermosphere is kind of atmospheric, this is what we would need to do to study it. And this is, in my mind, fine. We're going to have a lot of horse trading and discussions about what are the right instrument pairings, what's the right mass dedicated to studying the magnetosphere, and break that down and fight and cry about the instrumentation. and the capabilities. We want to answer detailed science questions. But those are not detailed traceability matrix questions. They are not hypothesis tests because we don't have enough data yet. So it's a mission of discovery as well as requiring us to come up with a lot of model context and hypothesis-based questions that we can determine our instrumentation requirements from. It's going to be a hoot. I think we should all go in the room, boxing gloves ready, and walk out with a magnetospheric mission, because in my mind, that's the most interesting thing about Uranus. And it is a flagship mission, so we have a bit of mass, and we should do it right if we're going to go all the way out there. In conclusion, this is all the things I just said on the last few slides, but mashed into one slide. So don't read it, it's fine. It just says, we've got this great natural plasma laboratory at the edge of a dynamic range, right? That figure up there is maybe my more favorite one, because it shows increasing diurnal variability and increasing seasonal variation. And there you see all the magnetospheres in the solar system, and Uranus is out here on the most extreme for both of those dynamic ranges. I think that's the compelling sell in terms of why it's a fascinating asymmetric magnetosphere to go and study. It interacts with moons. I didn't even get to talk about the moon interactions and ring interactions because I wanted to keep this solely magnetospheric. But take that complex tumbling geometry, or that nice magnetic wave geometry I showed you for Jupiter, and complexify it, if that's a word, by a lot due to the asymmetric magnetospheric geometry and the high obliquity at Uranus, and you get a really wavy system to study icy moons from a particles and fields perspective, which is the right one to have. So I would say that there's a lot of cross-disciplinary science questions that necessitate observations from multiple perspectives here. If we want to understand the magnetosphere, we need to understand plasma sources. That means moons, rings, ring atmospheres. If we want to understand Uranus, that's the thermosphere, atmosphere, and magnetospheric question. We need UV aurora, we need infrared aurora, we need particle precipitation measurements. There's a lot of cross-cutting, cross-disciplinary science to be done at Uranus, so I think we should go and do it. I'll leave it there.
Thank you so much. So we will start taking questions.
So I'm surprised you didn't talk about Jamie Jasinski's report at the Mach meeting.
I wanted to talk about it, and I looked high and low, and it's not published yet.
It's not published yet.
And so I didn't feel like I was allowed to steal slides that he shared with me from his meeting presentation if they're not out there in the real world yet.
Well, it was a public meeting that was
It's
also
a public
recorded.
Meeting, and it's a public abstract. So I can say definitively, Jamie had a lovely talk at Mach that I've referred to personally many times about the fact that, as I alluded to, the magnetic field in the solar wind was stronger than anticipated upstream of Uranus.
And the magnet and the plasma
and so Jamie's
pressure was higher.
Gone back and looked at the plasma pressure as well to indicate that perhaps when we flew through Uranus's magnetosphere, it wasn't a nominal magnetosphere, but one that had been experiencing or just experienced a very enhanced solar event, and that the magnetosphere, hence that we saw, may have been one significantly out of equilibrium, right?
Right. So it had been sort of all of the plasma had been flushed out. And as someone who analyzed the plasma data at Uranus back in 1986 or after 86, I'm appalled that I didn't realize this at the time. We are actually reanalyzing the data, Rob Wilson and our group, and we are going to be thinking about this as we go back. But it's pretty amazing. And I'll just give you everybody a hint that at Jupiter, this past couple of weeks, we had a huge coronal mass ejection that may have reduced the size of the magnetosphere from 100 RJ down to 30, which is the smallest ever seen. So this idea of taking a large magnetosphere and emptying it because of the solar wind, that damn solar wind, that just pushes it all out, flushes it out, and then it refills again. So definitely Uranus, let's go back and go see what it looks like under other conditions.
That's a great.
That would be fascinating if there was a CME with that kind of strength. Right?
Sorry to make you get
No,
your
you're.
steps in.
Oh, don't worry. This is nothing yet.
Thank you. Really interesting talk. You showed a slide with the plasmasphere in a quadrupole at Earth. I was wondering if you could speculate a wee bit on what that could imply out at Uranus. Because what that makes me think is if we have a quadrupole plasmasphere with our low energy plasma in a different plane than Voyager sampled, could that mean we do actually have our low energy plasma and maybe a source population for our radiation belts, or do you think something else could be happening there?
I think that's a great question, and this is the limitation of a single flyby. Now, I will say during that flyby, Uranus was rotating, and that means that whatever those equators, and maybe not a typical dipole equator, but whatever those convection style, co-rotational style equators look like, were rotating and should have passed over the spacecraft a bit during its trajectory through, just like in the tail, the neutral sheet was sweeping over. But I think that a really deep reanalysis and close look at the plasma data is in order. Ian felt that he saw an asymmetry flying from one side of the magnetosphere to the other and sourced a plasma population there. Is that source that he found in between Miranda and Ariel sourced from one of them and radially transported? Or is it us crossing through the equivalent magnetic equator where plasma could be trapped? I think these geometry questions are really complex. Even in his paper, he was injecting particles to see where they would evolve at the magnetic equator of the off-centered tilted dipole, which may or may not have been sweeping over the moons at all. The moons are going to maybe emit plasma whenever they source plasma, but the magnetic equator is going to be sweeping over them in a complicated way. So just injecting them at the magnetic equator only is probably not the right way to track them, even though we're used to and conditioned to doing that at Jupiter, because the moons are always within 10 degrees of the magnetic equator, right? So it's a complicated thing, and it might well be important. But maybe only out, I think still this calculation of where are those effects most important, maybe only out to 8 Uranus radii, or maybe is it 4, or maybe is it 12. Really understanding where those fields are dominant and will affect things is going to be an interesting and complicated modeling study unless we can get some real data in there to support it. And we'll have to wait on the data, let's be honest.
I have a quick one, and then I'll come back over here. In terms of the tail reconnection, like the DiBraccio and Gershman study, although it might have been the other way around, I can't quite remember. Is there anything we can tell from tail reconnection that would inform us more about the quadrupole? Or basically about the moments? And I'm sort of thinking out loud right now. I don't
think so. The tail reconnection was observed pretty far down tail, at least from the one that they found one by doing a very detailed eigenvector reconstruction and analysis of the data. They found one that looked like a plasmoid. It was pretty far down tail. I think more what we're going to learn about in reconnection in the tail is the cyclic loss of plasma down tail and how a helical tail will enable and where it will enable that reconnection to occur. It's not our typical substorm thinning of the plasma sheet, release of plasmoid dipolarization picture when you're dealing with this helical structure.
Okay. I think we have a few questions over here.
I have two quick questions of curiosity. Very interesting. Number one, what's the plasma beta in the Uranus system? How fluid is the magnetosphere? Or with all the flopping and things like that, are kinetic effects thought to be super important? And then the second question is ion escape a thing that people think about? You would expect that question from me, but here it is.
I would expect that question from you, indeed. I think both are great questions. I think in terms of plasma beta, if you have basically no plasma, that's your answer in terms of what it's magnetically dominated, right? But I think Fran gets to a really good point. I don't know that it's always that way. I think we saw it that way, but we also crossed the neutral sheet, and the neutral sheet had some stuff in it, and even though it was far away from Uranus, and so we know stuff had to be there to provide the stuff down tail, if that makes sense. So it's interesting. What we observed in the inner magnetosphere, there was not much plasma, and therefore it's magnetically dominated. That's the way my brain thinks about plasma beta. We do have faint weak and occasional and not fully structured in the way we're used to seeing auroral structure. I mean, definitely nothing like Jupiter, but maybe even nothing like Earth. It may be that it's cusp aurora, and that was a reference I didn't throw in, but there was a recent paper by Drew Turner. Yes, thank you. Brain stopped. That looked at cusp aurora. What did you say, Fran? Yes. Okay. Yeah. I mean, again, it was a wireframe. It was a toy model. It wasn't a dynamic model. It rotated a magnetic field, looked for where reconnection could occur, and then mapped that down and said maybe that would be a spot in basically a cusp type aurora. But again, we don't have a lot of data points to go off of in terms of the aurora either. Maybe now, being near solar maximum, would be a good time for us to be pointing UV telescopes at Uranus to see if the aurora enhancements make it more clear what that structure looks like. More photons. Ionospheric outflow, I don't know. I mean, I stick an ionosphere on the model and let it go, and some stuff comes out, but I don't. It's not well constrained. So.
Any other final questions? Otherwise, you are able to come and speak to Professor Paty after. Okay, just kidding. Last one.
Okay, magic ball time. Assuming we can get a mission out in this decade, can we get there by February 9th, 2050?
Very specific number. Yeah, okay. Sure. I mean, this is Corey Cochran's model. I think his name might have been darked out on this screen because it's blue on black. But that's just an idealized time frame that he ran his little wireframe model there to show us what it looks like. I mean, we need to get
going. What is the cruise period?
Now, well, optimistically, Fran might remember this better from the decadal than I did, but optimistically, if we get the Jupiter gravity assist, we could smush it down to 13 years. Is that right? Or bigger rockets. Those add risk, Fran. They don't like risk. I told them you could get to Neptune faster if you used an SDP or other kickstart stages, and they said too risky. Or you could stick it on SLS. If anyone has an extra $1 billion, we could just shake Elon Musk upside down and use whatever fell out of his pockets to buy another SLS.
All good food for thought, yeah.
Yeah. I'm all for shaking him upside down for a bit. And I'm grateful because we had SpaceX launch Clipper. Grateful that we had SpaceX launch Clipper.
On that note, I think, please thank our speaker. If you have any questions, she'll be around for just a few moments, and then we have a few slots open tomorrow on her schedule. You all should have received that email. Thank you for coming, and please go vote.
Yes, go vote. Also, don't be afraid of Uranus. Just because it's the butt of many jokes